RG for LSS. So the idea is to understand basically, okay, so what's the question that we have? Is basically to understand how the main LSS objects, like fields, like the density field, or the velocity field, or endpoint functions in general, change as a function of lambda. So this movement scale that you have. And the solution for this, we know from high energy physics, is basically the whole renormalization group set of like the whole framework. And the reason why to do it, I mean, why to consider this, the renormalization group itself, is because we can basically import the whole QFT techniques that we've been using, like, for instance, like, and also the FT gains, for instance, this interesting UV IR connection that you can have, thinking about, for instance, the relevance of the operators that you have, also resumming higher loops and large logs. So my idea is to explain to you a bit like what's the analog of those logs in the context of LSS, if they show up or not, and what exactly you can gain from this.
Sorry, in quantum field theory, you have to do it. It's not that you want to do it, you have to do it. Do you have to do it here too?
Well, you can still do like a perturbative calculation on a fixed loop level, right? I mean, for some cases, you still, I mean, you have to resum part of the large logs as well, right? Some of the large logs, yes, you have to compute it to gain part of this information.
I mean, when I learned, I don't know if the subject has changed, but when I learned it, it was because the parameters that appear in the Lagrangian are not the physical experimental parameters. That's why you have to use the renormalization group too.
No, renormalizing for sure.
I thought it was on the microphone. I think it's on. Okay. Okay, sorry.
For sure, you have to renormalize the operators. But considering the Kalin-Semantic equation, the reason why you do it is also to resum part of the higher loop.
So you have to do it here too. It's not like you want to do it because you can do it in quantum field.
Renormalize the operators, you definitely have to do it.
Okay, so then it's necessary. If you
renormalizing is necessary, but like considering the Kalin-Semantic equation is not strictly speaking necessary. You can add a fixed order and a fixed loop order, consider it like renormalized operators, and measure things for one fixed loop order. But you don't have to do it. Renormalization, for sure, you have to renormalize, but considering how things evolve as a function of scale is something else, right? One thing is to make everything finite and predictable. This you have to do, of course, but the other thing is to consider resummations from higher loops, right? or like large log resummations.
So I'm not sure I get it. So there are tools you can use to resum. Is that what you're calling the renormalization group?
Yeah, like the Kalin-Semantic equation.
Okay, when I learned the Kalin-Semantic equation, it wasn't to resum, it was...
Yeah.
Okay.
I mean, you know,
it's just a beta function equation.
At some scale, in order to find things at another scale, principally.
Yeah, but I didn't use it to resum different loop orders.
The large logs. Yeah, you resum part of the loops, right? There is a piece of the loops, specifically part, like you can decompose every single loop. I'm going to explain better this.
Okay, so I'll let you explain.
So I'm going to go through this exactly like this. Right, so the plan for this talk is to go through this QFT intro in which I'm going to try to dig into what exactly is resummed in the context of QED in specific, just as a trivial example. Then I'm going to go through the basis of operator, explained that yesterday already, but just to recap and define better what I mean. So C, I'm going to explain single and double hard limit of those operators. So basically, if you consider the RG, you're thinking about how things change as a function of scale. So if you take those operators and take one specific limits, like limits of those operators, this should give you basically the RGs, which is the topic of the fourth part. Then I'm going to talk about solutions for these RGs, for this set of ODEs that you have. And finally, in the last part, what we can gain from this, okay? So let me start with a QFT intro. And I'm just going to talk about defined structure constant. Alpha here is a function of mu, mu being a renormalization scale that you fix. So if you use dimreg together with MS bar, you have that you can derive the Kalin-Semantic equation for defined structure constant as a function of mu as being a beta function at one loop level, which is just a number times alpha square plus a beta function at two loop level times alpha cubic plus something else that is ordered alpha to the fourth. Specifically, beta one loop is equal, you can calculate this, is equal to 2 over 3 pi, and beta 2 loop is equal to 1 over 4 pi squared.
What's the theory?
Sorry?
What QFT are we talking about?
QED.
Electron.
Yeah. U1. Okay? Right, so with this equation in hand, you can consider the leading log, what we call the leading log solution. So the one loop solution for the RG is given alpha by alpha of mu. You can just solve this equation at a fixed alpha star 1 minus beta 1 loop, a log of mu over mu star. This alpha star is something you measure in the IR, so this is the typical 1 over 137, approximately 1 over 137, that gives the whole, spectra of fine lines in the hydrogen atom, for instance, and so on and so forth. So we can trivially expand this solution here as something as alpha star 1 plus beta 1 loop alpha log of mu over mu star minus beta 1 loop squared alpha squared a log squared of mu over mu star plus dots. And this piece here is what we call the one loop piece. And this piece here is a one loop squared piece that belongs to a two loop calculation. So if you want to have something like this, this basically is a two loop comparable order because it's order alpha squared. Okay? So
there's an alpha in there's an alpha in the first denominator, in the top denominator,
so
multiplying beta.
Alpha is not in the denominator here. So it's an expansion in alpha. Just because alpha here
Looks like
alpha is small.
Looks
right?
like when you expand. Looks like when you expand the 1 over 1 minus beta, you get a 1 plus beta alpha. So I think shouldn't there be a beta 1 minus beta alpha log mu in the upper denominator?
There is a beta here. Maybe in the camera.
Isn't there an alpha? Isn't there an alpha multiplying that beta?
Ah, there's an alpha. Sorry.
Yeah, it was the same.
Sorry. This is the yeah. Yeah, you're right. The beta alpha beta here, right? Yeah, yeah. Thanks. So just in terms of counting. So the powers alpha to the L are given basically by the L loops, right? And what comes with alpha L, some log to a power L of mu over mu star is what we call the leading logs. So what's the idea here? The idea is that we compute the one loop RG and we find a one loop solution, and if we plug in this one loop RG solution, if you do a tree-level calculation with these ansatz for how alpha evolves as a function of mu, you're naturally resumming higher part of pieces of higher loop contributions. So this is the whole idea of the RG technology. If you do a tree-level computation with these ansatz, like basic for alpha as a function of mu, you naturally gain higher loop pieces. Okay?
Can you just draw the diagram of that one loop square, just so I understand what two loop piece you're talking about?
This diagram here.
Yeah.
So, okay, let's go for diagrams. So this is something like this that we have, right?
Yeah, that's tree level.
Yeah, tree level goes for
Okay,
this. So this piece should be something as, so this has another power of alpha. So this should go as something as, what's the typical one loop? So you cannot have vertical. So, sorry, so So you can only have one here, right? So it's QED. So. Ah, okay, sorry. Like this, right? Ah, right, okay, so yeah, so this is the cut you have, right? So you had these legs, so this is the tree level one, and we basically merge those two. So this is the two level piece, so it basically have something
I
that's
don't think so. I think they should all be,
like this,
they
right?
should all have two electron or, I mean, they should all be the same type as the tree level, right? You're correcting the tree level. They should all have 3 external legs, I think.
Okay, so, okay, yeah, thanks.
Okay, probably you don't want that other one, just the 2.
Well, for the tulip, you need this, no? Like, or
Yeah, probably, that's a 4-point amplitude. I think you're looking at a 3-point. So I think I understand what, so you just add more and more loops that don't talk to, that they're just in that, like, sequences, right?
yeah, so this piece here would be something like alpha square, alpha cubic. So this should be, right, tree level, sorry, like tree level is something like this, right? And then keep
Yeah.
plugging.
So you just keep adding a loop in that way. Is that right? Is that what these terms do?
Yeah, exactly, I think so.
Where the loops are nested, right?
Well,
so you can think a correction to this that is probably what you call inside the 2 loops, right? Is where you make another loop inside the loop.
Another loop inside this loop.
Yeah, that would be what you call truly two loops.
So there's a piece that's the true, like the true loop would be something that also contains the next 2 leading order logs.
How do we know
So
that?
piece of this diagram, so it's just, so these pieces here are just a limit of this diagram, some momenta region. So in the whole phase space that you have, like the whole phase space integrand that you have, these logs just correspond to one specific momenta regime of those loops here. So it's not that exactly like, it's not that, you know, it's not a new diagram, it's just part of these diagrams here. It's just in the phase space of these diagrams, there's this piece that's embedded here as a momentum.
I see.
So
I
the
see,
question
I
is
see,
how
I see,
important
I
this
see.
piece is, right? So the question
I
is
see.
this piece becomes important when these logs are large. So when the scale you are is larger than the IR scale, which is the IR scale. So when the scale of the measurement you have is larger than this mu. Well, that's the idea of resumming, right? That's why you need to resum them. That's why. So define exactly when you do this, when you resum everything using these ansatz, like here, the solution for the RG. Basically, that's exactly when you need those logs. When those logs become large, you actually need to resum them, right? You need the RG. That's when the RG is a must.
You know that have a Landau pole, right? At one loop, so you have to be careful.
Right, but this. Yeah, but then you have another scale, right? You have. Right. So then you can, of course, go to next leading order and consider alpha mu of next to leading order. Okay, I'm not going to write it down, but the idea is that you have another piece here in this equation, and when you consider it, instead of okay, so here is leading log, but you have a next to leading log piece, which would be corresponding to summing here, something that's proportional to beta 2 loop alpha square log of mu star. So that's where we can see that this is the main piece. When this piece here that has an extra power of log, so comparing to this piece, this has an extra piece of log. So when the logs are large, actually this piece of the loop becomes the most relevant one compared to the next to leading log part, okay? Sorry? Yeah, we have one loop beta here, and this is a 2 loop beta.
You have to know that they're of the same order. That's when.
Right, and here we
One
have,
may be
okay.
0 for some reason.
But those are parameters of, that are order 1-ish.
Yes.
So in the case of QED, there are 2
I
over
see.
2.
Okay.
Yeah, of course, I mean, but you have to compute the loops and check if they're. But there is no parametric, I mean, if there is no parametric parameter that controls it. So. Right, so schematically, we can organize those loops. Generically, we think about loops. If you think about a cross-section calculated at L loop order over cross-section at tree level, we can write it down as some alpha to power L C L L log of L plus C L L minus 1 log L minus 1 and so on and so forth, right? So exactly what the RG resums for you is if you have something like, okay, a tree level contribution, it's a trivial statement, of course, but it's alpha to the 0, C, so some coefficient. So this C here is just a number, like a coefficient. Log to the power of 0, a trivial thing. So the one loop over a tree level contribution is equal to alpha to the first, what we call C11. So 0 stands for 0th power in alpha and 0th power in the log. And this has a power of log 1 plus C10 log of 0. And you can go on like this, right? So what the RG gains for you is exactly if you use a one loop RG, the gain is exactly from resumming all the terms in this column here. And if you use the two loop RG instead, the gains is from the next two leading log in the higher loops. So what it means is that you don't have, I mean, when the logs become large, you don't have to compute the whole loops. Part of the loop information is absorbed already into the resummation that you gain by one loop result. So you can use a tree level result, measure these C's here, use a one loop result, which is, I mean, in this case, just the solution for the one loop OE, plug this solution back, and basically the C coefficient that you have here is fixed by this equation. So the C coefficient in this case would be basically this one here. So this would be C11. Right? Sorry, it has a log square. So this would be the C22 actually. Sorry. So this would be C22. And this would be C11. Yeah. Okay? That's exactly the idea. When the logs become large, you actually can gain part of the loop phase-space regime. Questions? If we're missing part.
Can one think an example where, maybe not QED, where doing this will miss the main value of the calculation?
Well, you don't have to think about another example. It's just a case of QED in the regime in which those logs are not large. Right? So this means you have to compute the loops. So this means you have to go through the whole cumbersome calculation of computing the higher loops, right?
I see.
Thanks. Okay, so part B. I'm going to focus now on the basis of operators. I just explained yesterday how we construct these bases on top of the symmetries of the problem. Just to recap here, because I'm going to use part of the notation throughout this talk. So in the case of LSS, we've seen that, okay, we construct operators on top of, we have this generic delta G, which is a tracer of matter, and we construct all possible operators as derivatives of the gravitational potential. It's slightly more complex than this in reality. I'm not going to talk about it. But this is not the single guy allowed. There is an extra guy allowed. Yeah, so, I mean, this was the idea yesterday to flash the slides here, but I can, of course, dig more here. So in the case of, okay, so let's go through this. So we know we want to understand basically how, what we've derived equations for d tau of matter equals something. So these the equations I was showing yesterday, right? So the fluid equations. So the idea is that we have equations for matter, but we don't observe matter. We observe galaxies, delta Gs. So the question is how to relate. We know matter. We can basically relate matter via Poisson equation to the gravitational potential, right? So this is Poisson. So we know that GR only allows, since the symmetries of the problem on large scales, it's basically GR, it tells us that we can only include operators that are basically two open derivatives of the gravitational potential. So this is the most generic symmetry of the problem, the only symmetry that we have in this case.
So that's probably obvious, but can you just explain what you just said a bit slower?
This part here?
Why being GR means that you can have two open indices?
Oh, this is equivalence principle.
What is that?
So equivalence principle.
Let me maybe phrase the question like this. So normally we would say that when I write an effective field theory, if I have a theory of a metric, I should build curvatures and so on, and those are the objects. And then I can use curvatures to build whatever I want.
Yeah.
So here I'm not used to discussing this phi. Phi is some element of the metric or something like that, right? So
Yeah, okay. Phi.
So it's something that when we say GR and then we mention phi in the same sentence, to me it's confusing me because it looks like the opposite of being covariant. So
phi is the perturbation in the metric, right? So this in the context of cosmological perturbation theory, phi is basically the leading perturbation in the metric that you have. The gravitational potential. This is what we call Bardeen potential. So this is when we do something like ds square, we have something like 1 plus phi dx. So there is a part here that has a minus d tau square plus, I think there is a minus, I don't know by heart, but so this would be the dx square piece. So this is the perturbation in the metric that you have.
And then just remind me, so the statement is that if I compute Ricci scalar and so Ricci and Riemanns and so on, they will be built out of the IDJ phi, and therefore using the IDJ phi is like using curvatures. Is that the statement?
Yeah, exactly. So this is the gravitational potential, and everything should come, I mean, in principle, there is another degree of freedom psi. There are 2 degrees of freedom here, but when you consider in the absence of what we call anisotropic stress, you can basically set one equals minus the other, so there's only 1 degree of freedom here in the metric. So in this case, this is the gravitational potential that depends on x. So there is there are some scale factors missing here, right? But this is what we call, okay, so this is basically what sets the whole perturbations in the universe in the context of cosmology.
So should I take this metric and build curvatures with more and more derivatives and see what they become in terms of phi?
Yeah, you can do that. So you can compute basically the Ricci scalar and the Ricci tensor, okay? And you can do all the whole GR calculations on top of this phi, and this basically gives us, okay, from Einstein's equation. So what enters here is basically, so this G mu nu is a function of phi. And here on this side, we have matter. So then you basically have a function that relates phi, the metric perturbations, with matter perturbations. And this is how you derive Poisson equation.
So we are doing effective field theory, right? So we are integrating out some degrees of freedom and seeing what remains at low energy, right?
Yeah.
So do I generate effective higher curvature corrections in gravity, and what are the low energy degrees of freedom, and which curvatures will I generate and which ones will I not generate.
Right, so we can split this phi here into a phi long plus a phi short. So the question is what's in this phi short and what's in this phi long here. So everything that's what we call phi long is basically when this phi is, okay, when this phi is smaller than 1. So when this guy becomes large, so when metric perturbations, so what sets when this guy becomes larger than 1 is exactly when the right-hand side here also becomes larger than 1, which is when the matter perturbations become order 1. So going through this side of the equation, so this is matter, right? So we also have matter perturbations, and this is what we call delta. So delta is what enters here on this piece. So when the matter fluctuations become large, so when the fluctuations in this field become large, this defines what this guy is, what the small scales fluctuations are.
I just want to understand what are the variables. So in QED, for example, I have the gauge field, and then there's this Landau pole, so I know I'm dealing with an effective field theory. So in fact, I have F squared plus F4 plus F6, etc., right?
Yeah.
But okay, the right variable is a mu, and then I have all this higher curvature correction. So if I were to write the equations of motion, for example, it will not be just Maxwell. It will be all the higher term corrections. But here, for example, you write Poisson, which to me looks like the first term, that there would be also a tower
Exactly.
of
So there will be
corrections and
so there will be
on.
corrections proportional to phi square here. So you have all next to leading order corrections. But since phi is small, you can drop those corrections here. So actually, you can show that the next to leading orders in phi are not relevant compared to, okay, you can just keep,
Okay.
on subhorizon scales, those are the leading piece that you have. It's a bit complicated, but so the degrees of freedom, you can imagine this as being matter fluctuations. You have matter fluctuation and you have gravity fluctuations. And they're coupled via Einstein's equation. Okay? So inside the horizon, deep inside the horizon, there is only one single degree of freedom because both are related. Oh, so when we think about vector and tensor perturbations, like specifically vector perturbations decay, you can of course have a further, okay, you can have extra terms here that are vector and tensors. But okay, tensor fluctuations we know are gravitational waves, which are quite small. We measure this to be small. Tensor, like vector fluctuations, just decay. You can derive an equation and you see that they exponentially decay. So we can drop them from the. So we only have two scalar degrees of freedom, which are phi and psi, and they're coupled in the absence of an isotropic stress. Yeah, sorry, I skipped many parts here, but this is. The idea is that we have the degrees of freedom that we have are basically these derivatives of phi, which are perturbations on top of the metric, the inverse metric, okay? You don't seem happy. Okay. So maybe I'll be happy to chat more. Okay, so the idea is that we want to construct general tracers, what we call tracers of matter. And this enters as the most general terms you can write as two derivatives of phi, and what tells us that it has to be two derivatives is equivalence principle. So you can only have two derivatives, and since this is a scalar, you want to construct scalars on top of those two derivatives. So the first thing you can do is to contract with a Kronecker this, and then you trivially get, after contraction with a Kronecker, you get an Abla square, and this gives you delta. So you can, okay, so let me write this.
A few times, but is it just what he said? Is it just that it only depends on the curvatures? Is that what you mean by equivalence principle, or is there something that I'm missing?
What I mean by equivalence principle is that you can only have, you cannot have one derivative here.
I know what the equivalence principle is. I thought I knew that, you know, things fall like they're in an elevator and things like that. What does that have to, why was that related to this?
So it's related because if you, suppose you, I mean, you can try, right? You can try to write things like as the things
No,
constructed.
let's put 4 derivatives.
Oh, 4 derivatives. But this is not allowed, right?
I don't know, I'm asking you. You're telling me it's not allowed. I'm
I
asking
mean,
you
for
why.
allowed. Well, in principle, for derivatives, you can take more derivatives here, of course,
Okay,
right?
that's all
It's,
you mean.
it's fine,
Okay,
like, but
okay,
this,
that's
this
what you
comes
meant.
as higher
You
derivative
don't mean it only
expansion.
has 2 derivatives.
No,
You
no,
mean it
minimum
has-
2,
it has
minimum
at least
2.
2 derivatives.
At least 2.
That's fine. That's
Sorry,
fine.
sorry, sorry. So what I mean by those O's are exactly the O's that are constructed on top of this. So at first order, this appears as just a Kronecker contraction of the y del j phi, and this gives us delta. At second order, you can think about basically this term square, but we can also have the other term del y del phi, del y del j phi, del y contracted with another del y del j phi. So this gives something that we call the Galilean operator. I write a 2 here because there are other Galilean operators that you can construct on top of these, like third order Galileans. And you can go to third order, and there are actually 4 operators that you can construct here on top of this object. Okay? You can check and systematically construct a basis here. So this,
At some point, you mentioned simulations as a way of validating what you are doing. Can you just say what we would simulate? We solve those Einstein equations there, and
Yeah.
I think that would help
No, actually,
understand the UV.
actually, that exactly explains the first question, I think. So the question is, when can you separate this? So the question is, what's the scale that defines these small scale fluctuations and these large scale fluctuations?
Yes.
Thanks. Sorry. Yeah. Oh, yeah. So when we compute fluctuations, like you can do linear theory, and at linear level, you can just solve this Boltzmann system and like the fluid equations that you have, and get linear theory. At linear level, you know, you can calculate like this delta 1, what I call delta 1, which is just the linear solution of the fluid equations that I was talking about yesterday. So we define, okay, so let's define this. There is what we call K and L, which is the nonlinear scale that divides long scale mode and small scale modes. So basically, when delta 1 squared becomes order 1, this is what defines K and L. So delta 1 of K and L becomes order 1. This defines what K and L is. So you can check that the variance, so sigma here is just the variance of delta 1. When this variance becomes as a function of the smoothing scale lambda, so this variance basically grows as a function of the smoothing scale lambda. So when this sigma here, which is the variance, so it's a Gaussian field, this delta 1, right? So the PDF of delta 1, so it's a Gaussian field. So when this sigma of delta 1 becomes order 1, this basically defines this KNL. So you can use linear theory. So the perturbations in the universe grow in time, and when those perturbations reach order 1, and this KNL is a function of time, right? So no, the variance should increase. When you go to small scales, the variance increase. No, lambda is in, I mean, this is in 1 over megaparsec. Okay? So when you go to basically smaller scales, sorry, this is, yeah, I find K more intuitive than radius. So when you go to smaller scales, like large lambdas here, you find that the fluctuations in the universe become so large, and this defines KNL. Just to be clear, like the typical scales I'm talking about here is order 0.1 age over megaparsec. So you can compute. So you can, for instance, run simulations also in practice and check at nonlinear level when the variance becomes order 1. So that's why you need simulations to kind of compute. So at linear theory, you can, of course, predict exactly like when it happens using analytic calculations. But you can run simulations and also on-the-fly cross-check at the nonlinear level what exactly the k in which it becomes order 1. Okay? So that's why you need simulations, to actually cross-check exactly what's the value of KNL you have here. Okay? So let me go on here with this piece. Right, so generically, every one of those operators, O, we can write down as a function, as a sum using perturbation theory of convolutions of delta linear. So delta 1. Sorry, I'm going to use delta linear and delta 1 interchangeably. Like it's just notation-wise, delta 1 is the linear solution of the fluid equations I was talking about yesterday. So it's just convolutions of these delta 1s with some generic kernel K evaluated at some order in perturbation theory. So N here is the order in PT. So you have basically N entries here of delta 1s. So it's a convolution of those guys. So what you can see is that once you are at second order in perturbation theory, you have here, okay, there's another part here. Since you have a convolution in Fourier space, those are composite operators in real space, you have a Dirac delta here that fixes K minus Q1 minus Qn. So it means, for instance, that when n equals 2, we have something like, if you have Q1 and Q2 generating a K, you see that you have two small scale modes that can generate a large scale mode. So it means that you have to smooth out this equation at a fixed lambda. So it means that this operator here receives contributions from arbitrarily small scales, and they need to be renormalized. So what I mean by this is that all these bases here should depend on the smoothing scale lambda that you have. Because all the operators you have here depend exactly on this potential, and this potential exactly like you should smooth it when you take contractions of this. It's like composite operators. You should regularize this theory, right? Right, so this to say that this lambda here has to be added since the operators all receive contribution. From arbitrarily small scales. Questions? So now we want to, okay, now I'm going to move to part C, which is the single and double hard limits of those kernels K here that you have. So those kernels are basically contractions, basically different structures of this operator here that you have, momentous structures of this operator that you have. And since we have a complete basis, I want to check that by taking limits of this kernel. So when I take momenta limits, so this kernel depends on Q1, so I'm integrating here over Q1, Qn. So when taking limits of this kernel, I want to check if my basis is complete, and it gives me another kernel that's inside this basis as well. So if my basis is complete, by definition, all limits of this kernel should be also contained in the basis. So to be sure that I'm closed under renormalization, I have to check that all specific limits of this kernel here also have to be inside my basis. Yeah. Yeah.
We don't start writing kernels, convoluting in complicated ways. But here, can you explain the difference between...
No, but this is exactly the same. We are doing the most general things we can write. So
when I do pians, I don't see things like this. Why don't I see things like this when I study pians or flux tubes or gravity?
But in this case, why do you say it's not everything you can write? Like, this is everything we can write in terms of derivatives of phi. What I mean is that delta 1 is related to del y dj phi via Poisson equation. So you can do linear theory here, and you say delta 1 is equal basically to del square phi 1.
Yep.
In the Galilean?
Yeah, that's what I mean. So the Galilean is a different contraction, right?
Yeah.
So how does that appear from that?
So the Galilean appears when you take del y del j phi 1. Yeah, let me write down somewhere else because... So the Galilean is equal to del y del j phi 1, del y del j phi 1, contracted with another del y del j phi 1. That's why I can use linear theory, like it's just another momentum structure of this del y.
No, the question, I guess, maybe is the same question as there. How do you see that from that generic form? How do you see this appearing from that generic form?
So this generic form, so this k is exactly this momenta that you have here. So this k is exactly what you have in this del y del j. So this would be just k, q1, q2, like the product of q1 and q2.
So you mean di, dj are part of the kernel?
Yeah, exactly. This kernel, like, for instance, I can, so this k, there is a label O here, sorry, missing. So k g2, I can define a k g2 that is exactly equal to, okay, it's going to be equal, just using this formula, it's going to be equal to something like, this depends on q1, q2. And this is equal to q1, q2 square over something like q1, q square, I think. Something.
All right, thanks.
Okay. Does it explain?
Yeah, yeah.
So you see, it's just, yeah, it's just products of momenta that you have. And these products, like these ratios and products like and sums of momenta are given basically by this contraction. And you find the solution of the linear one just by plugging in here, and you can ask your Boltzmann solver like Camden class to calculate this delta 1 for you. Okay? Right, so if I have a basis that's closed under renormalization, I have that basically limits of my kernel are also in the basis. So what I call single hard is exactly one single regime. Okay, I have an operator O here with multiple delta 1 legs. So I have delta 1 legs here, and I know that if I take one of the, like 2 of the legs, contract them, and take this P and bring to infinity, this should be another operator O prime that's also in my basis when I take this P and bring to infinity. So this is the single hard limit of each one of those kernels here. So if my basis is closed, I have that for every single operator, K, O of P minus P when P goes to infinity should also be in the basis.
So any effective field theory, I write everything I can write, and that's it. That's the rule of the game.
Yeah.
Are you saying something more than this?
No, no, exactly that.
So why are we saying anything if it's just this?
What I'm saying is that, okay, also I'm writing everything I can, and that's it. That's my effective field theory. But now I want to derive the renormalization group equations, right? So to derive the renormalization group equations, I have to take the single hard and the double hard limits of each one of those operators. First, I wrote down all the operators I could. So here I'm writing down all operators I can. Now I'm checking, I mean, if I take limits of those kernels, by definition, if I have an effective field theory, limits of those kernels should also be inside this basis, right? And I'm just going to use the single hard limit and the double hard limit to derive the RGEs. That's what I'm saying. I'm not saying anything more than it's an effective theory and I included everything in the basis. Now I'm going to take limits of those operators in the basis and check how they transform inside this group symmetry. Okay?
Are you going to write an effective Lagrangian? I think that would be helpful.
No, no, there's no Lagrangian here in this case. Actually, like, so this is something different than...
Some effective equations of motion.
So we write down the effective equations of motion.
That's fine. Will you write them down?
So this is what I was showing yesterday. Like, those are the fluid equations. So the equations of motion are exactly the fluid equations, which are so this is one of the equations I wrote down yesterday. So this is continuity. And you also have Euler's equation, which is something else for this theta. And you have something here which is nabla. Okay,
so those are, I can think of these equations as the UV, right? So these equations describe everything.
Yeah, those equations describe everything that I have. But there is a piece missing here in the right-hand side of the velocity.
And this is the stochasticity.
Not just the stochasticity, but the small scale fluctuation. So there is the sigma ij, which is the stress energy tensor that you have. So this describes basically shear. So this describes the small scales. And this is the piece I dropped yesterday. So there in the right-hand side of velocity, like equation, which is Euler's equation, there's a piece which is sigma ij here, which by considering a perfect fluid approximation, I set to 0. So what I'm doing here is to slowly add corrections to a perfect fluid approximation.
Okay. So if it was not, this term is the crucial thing, right? Without this term, all this discussion would not make any sense, right? So it's about, there is some extra term.
Yeah.
And the physics of this extra term, can you say it again, what it is?
The physics of this extra term are basically corrections from, when you dig into small scales in a fluid, what are the corrections to this? The first correction are sound velocity, the sound velocity of this fluid. So those are corrections to the perfect fluid approximation.
And so those corrections are just, again, everything I could write, right? So I just write, now I do effective field theory.
So this sigma ij is exactly a sigma ij of del I, del j phi.
Great.
Exactly.
So you just write everything you can write with unfixed coefficients that you fix by matching with what?
Then I match this with data. I just let those coefficients free and I feed them with data.
Not simulations, data.
Well, you can use simulations to get ansatz.
But I thought simulations you don't know because you don't know these terms.
So in simulations are exact. But I cannot simulate baryons, for instance. Baryons are super complicated. There are things I cannot simulate. Or I can have some ansatz on how to simulate. So that's why in the end of the day, we leave all those coefficients free and we let that data tell us the values of those coefficients. But you have to marginalize over those coefficients. Is it more clear now?
This is much more clear than this. Yeah, so I write fluid equations and then I add all the viscosities and so on that I could write as usual.
But it's important to say that this is for matter, so there is no index G here. So this is matter only. Right? So matter tells us basically how this guy looks like, right? So how this guy on large scale looks like. So how phi looks like is basically via Poisson equation. And matter tells us how this guy looks like. And then I take I take the solutions for this phi 1, and I construct general operators for this delta G, which is a tracer of matter. Because in the end of the day, what we observe in the universe is not directly matter, but tracers of matter. We observe galaxies, for instance. And galaxies are way more complicated than matter. You have, supernova stuff. You have injection of energy on large scales. You have a lot of complicated hydro and baryonic physics happening that we want to marginalize over. We don't know about. It's like, complicated hadron physics that we don't know about, and I want to integrate out. No, phi depends on time. So here phi depends. So phi depends on, we know exactly how phi depends on time, which is the growth factor. We know at linear order, the growth factor decides on how phi depends on time. So this guy also depends on time, sorry. What I meant by, if I said this doesn't depend on time, I mean this phi definitely depends on time. But we know exactly how it depends on time. It's just the linear solution for the growth, what we call growth factor, is basically, yeah. The YDJ. Here? Oh, good question. So for time, okay, this opens a whole new 15 minutes explanation, but this is a good point. So in principle, it should also depend on time. But there is a way to write down all the time derivatives here as space derivatives. You can exactly, people have shown that you can write down time derivatives of this guy as space derivatives. So in the end of the day, they're related. You can use it's a one-to-one relation. I don't want to open this branch, but you're absolutely right. They could depend on time, but you can show the time formation of galaxies. You can write down as space derivatives as well. For what? For this? This is Einstein. So this comes from writing down the most general, you write down a fluid equation, the fluid equations that you have, and you show that all the time derivatives are basically intrinsically related to the space derivatives. This is, yeah, it's Einstein equation, and then it's Einstein equation. It's a, yeah. So if you want to know more about how to write this, there's a paper I can recommend. It's okay. Right. So what I want to write down here are just two simple expressions that tell us how things rotate in this by basis of operator when it takes part of the momentum regime and brings to infinity. So this is the single hard and the double hard limit. So for the single hard and the double hard limit, we know that if we take an operator B, like with a generic kernel KB of K1, so this guy is expanded at order n plus 2. I know this guy Kn P minus P. So this corresponds exactly to this diagram that we have here. If we take P and bring to infinity, just the closure of this basis tells us that we should have a coefficient CBA here, n plus 2, giving us another operator A that's 2 orders lower than this one here at K1, Kn. So this is the single hard limit of the kernels. And for the double hard limit, I have the same here, but at n plus 4. Then for the double hard, I would have another leg here. Same as we have here, but now I have P minus P, Q minus Q. And I take P and Q and bring to infinity. I average over P, the angles P and Q. And this tells me that this also has to be something like D, B, A, n plus 4. So those are just numbers. And this is a function of the ratio Q over P, K, A, N as well. So those are the simple single and double hard limit of those kernels. But the magic is that these D coefficients that you find for the double hard limit here, you can compute. You can basically take this case that you find here after constructing the whole basis of operators, and you can find exactly what the values of these numbers here and these functions here are. And each one of these coefficients of the double hard limit comes with a very specific form. So this is something we found, that each one of these d coefficients here are very specific, have very specific shapes that are d. So these d's of the ratio of p and q. So we have two momentas here, and this is proportional to a function. This is equal to something times one single function g of the ratio of the momenta, p and q. And this function g, what it does for you is to filter basically part of the diagram phase space. So when you compute the double hard limit, we did it, we computed this double hard limit, and we find one specific function g that is related to the double hard limit, that what it does for you is to exactly filter part of the phase space diagrams that correspond to the intrinsic two-loop contributions. So when you take the phase space, so this, how this g function looks like. So this g, which is a function of the ratio of q and p, looks like, so I'm just plotting the module of this function. So what it looks like is exactly like this. So when the ratio is close to 1, this function has a peak, and it's also symmetric over p and q. So what it does for you is to exactly filter in like the two-loop diagram phase space, you would have to integrate over p and q. So what this function does for you is to exactly filter the diagonal piece of this phase space. So within the diagonal part here, so this function has a peak. So what this, this is something we found, that when you take the double hard limit, this g function emerges, this g function of the ratio of the momenta emerges, and what it does for you is to exactly filter what we call the intrinsic two-loop contribution. So what I mean by this is that when you compute double hard limits of these large-scale structure kernels, you're basically isolating the intrinsic two-loop contribution from the off-diagonal piece, which are the one-loop square pieces. So you compute double hard limits, you find exactly the same structure and all those terms shift under basis of basic rotation, and you find one single function g that determines how those operators rotate. And this function g basically filters the diagonal piece in this two-loop diagram phase space, which basically moves out and checks that you only have basically the two-loop contribution, the intrinsic two-loop contribution. Okay? So that's what I wanted to tell in this part when I talk about the double hard limit. So this was the first time it was computed, so we checked, okay, what to tell. In the literature before, people were just using this basis, feeding the coefficients, and being happy with feeding the coefficients. What I want to say is that we are calculating now limits of those higher loops, or basically one loop RG and two loop RG, because now you find that when you take those limits, specific limits, you find one single function G that basically checks that you only have the two loop diagonal piece. Okay, and this is something that comes as a result. This G function is one single function that basically tells you how all the operators rotate when you take this region in the phase space diagram. And this G function that appears is basically something that's, again, related to the symmetries, like has to be related to the symmetries of the problem. Okay?
Are you saying that your original list was wrong?
No, actually it's complete. We checked that this list is complete. So what we did is to check, again, this was something that we checked, that if you construct all operators on top of this basis and take the limits, you again find operators like that were in the basis. So we checked, we certified that nothing is missing by doing this. But what I'm saying is, when you take those limits,
I'm just confused, why do we have to do it? We just make a list, we don't make a mistake, and it's correct. Why are we doing then other computations of taking limits or something?
to compute
What is the subtlety? Is there a subtlety in listing all the operators?
So
We just list.
no,
what we
you're
can.
completely right. Again, you can just list all the operators, fit for those operators, and be happy with.
Yeah.
But what I'm saying is, when you take limits of those regions, you find that sum of operators limit can be related to other operators limits. It means that if you use the solutions of the one loop RG, you can resum part of the higher loop contributions, which are exactly those part here. So there is a part, if you just use those relations I'm finding, you can resum these off-diagonal pieces. That's what I'm saying. If you use the RG equations, you can basically, you don't have to compute higher loops of those operators. Part of the regions of those higher loops is already fixed by the equations themselves. Okay? So you take limits of those operators, and part of the, you don't have, originally, what would you have to do? You would have to, if you want to compute a two-point function of these objects, you would have to expand cross products of these guys in loops. One loop contribution, two loop contribution, three loop contribution. What I'm saying is that since we already took limits of this, and we know how those operators rotate internally, and we know exactly how they rotate internally, part of the higher loop contributions of those operators is absorbed by knowing how they rotate internally themselves. So you avoid a cumbersome project like part of computing higher loops, because piece of those higher loops is already known by the RG equations.
Sorry, and the regime in which, so in QED we understood when these are important. Is there a similar thing here?
Yeah, so let me move to this.
Let me just ask, yesterday you talked about counter terms, but here you haven't mentioned them at all. Are they irrelevant for this?
No, they're not irrelevant. So the counter terms, when you compute it, when you take the limit of p going to infinity here, you have another piece here. So I just mentioned the leading piece here, but there is an extra piece here, which I hide, actually, which is something that's order k squared over p squared. And those are the counter terms you have.
Okay, and those are just put in by hand,
So those
you
you
get
can,
new parameters.
so they make new parameters, like, those are new parameters. But these, when I take p and bring to infinity, I'm going to have ratios of momenta here, p and q. And those ratios give me the higher order terms, which are the higher derivative terms, which are the counter terms that I have. Okay? Yeah, let me move to the next part, which is exactly the RG equations. You seem to have questions like the... Yeah, in this case, it's a bit different than like the usual field theory story, because you don't have like a Lagrangian you write down. You basically write down the equations of motion, and you separate large scale and small scales on the fly, basically. It's a bit different than the usual story of like QFT story. So let me move to the part D, which is the derivation of the RGs that we have. So we know that the derivative of these delta G's with lambda has to be 0, and this tells us that the derivative of my basis with lambda has to change exactly in the same way. So I'm just summing over A here as my operators change with lambda. So how basically this guy changes is basically the dual on how the operators themselves change with lambda, right? And I can take contractions of this. So to derive the RGs, I can take contractions of this operator with delta linear. To derive the RGs, and I can expand dB d lambda into dB d lambda one loop plus dB d lambda two loop, and so on and so forth. So this tells us that if I plug this guy here, this tells me that dBA d lambda at one loop OA delta 1 at tree level. So I'm just taking the one loop here, tree level here. This has to be equal to a minus sign BB d lambda of my OB, delta 1 at one loop. So here is, okay, a tree-level guy, a one-loop guy, a one-loop guy, a tree-level guy. So this tells us exactly the Kalan-Semantic equation at one loop level, right? So I can use this to derive the Kalan-Semantic at one loop level. I can just compute those correlators here, and this tells me that at one loop level, I have that dBA d lambda at one loop is equal to minus b, some coefficient, so I can use this part here to take this derivative of with respect to lambda. So this tells me that this is some coefficient b, some number, okay, the bias b with some number ba as one loop, d sigma square d lambda. So what appears here is that, so this is the Kalan-Semantic equation at one loop level, and this tells me that at one loop, I have just coefficients, like number that I compute. I can use Mathematica. They just take the one loop single hard limits that I calculated here. So those are exactly the same. So those S that you see here are actually related to the C coefficients that I had here, and S one loop AB is equal to n plus 2, n plus 1 over 2, CAB, n plus 2. So by taking the single hard limit, I computed these C coefficients here, and in the Kalan-Semantic equation, I find exactly that the same coefficients appear than what I found in the single hard limit case. And this is again expected because this is how it should be like if my basis is closed. Right, so if you move to two loops, you can derive the Kalan-Semantic at two loops. I'm not going to derive those equations, but if you derive the two loop piece, I find that this guy is proportional to this G function that I had there. That's a proportion to Q over P. So exactly what it tells me is that the RG equation at two loop is proportional to this diagonal piece of my phase space. So exactly like the two loop piece is what comes in this intrinsic two loop part. And this is something you can derive, we have derived. So let me move to the, I think I have gone over time, but 10 minutes? Okay. Let me move to derive the takeaway message of this. Why are we doing it and what do we find? So the main message is that when you compute basically the ratio of the two loop and the one loop, let me flash some results here. So this is how the bias evolves as a function of lambda. So this is one of the bias. And we find that when you compute the one loop piece, it goes as this. And when you compute the two loop piece, it goes smoothly close to the one loop piece. It goes off when sigma square is order 1. But you see that the two loop is really close to the one loop. So what does it tell me? It tells me that the two loop piece, the two loop RG, is smaller than the one loop square piece. So when I compute the two loop RG, it's actually way less relevant than the one loop RG. So what it tells me is that when I compare those two pieces here, this one is way larger than this piece here. Which means in practice, what's happening is something analog. I will discuss this in more details like in the paper, but it's something analog as the large logs that we have in the context of QED. So the point is, this piece, when you compare the running of those terms, the one loop RG is actually able to absorb the most relevant piece compared to the two loop RG. So what it tells us is exactly that these off-diagonal pieces that you have here are way more relevant than the diagonal piece that you have here. Indicating that if you use these RG ansatz, like if you just take this equation, do a tree-level computation with this equation here, you're absorbing higher loops by doing this. And this part you absorb is actually the most relevant one when you compare the one loop and the two loop. So what we want to do is to use these ansatz here now. So what I showed yesterday.
Sorry, that, I missed something. So when is it the most relevant?
So exactly in the regime in which perturbation theory works, in which sigma square is smaller
but
than 1.
that's just tautology. I mean, it's relevant when in perturbation theory works, but
No, it cannot be. It's not supposed to be true. Like I mean, it cannot. There are situations in which this is not true, definitely.
Maybe I don't know what you mean by perturbation theory. So you're saying whenever perturbation theory works, the one loop, this term is more important than the two loop?
So the one loop squared, which is in principle same order as the two loop, right?
Well, it could be, yes. There's
so
no reason why it should be smaller or bigger.
So in
yes?
terms of the expansion parameters, one loop square has the same numbers of delta 1. So this is proportional to delta 1 to the fourth.
Okay.
And this guy is also proportional to delta 1. So this diagonal piece is also proportional to delta 1 to the fourth. So both are same order in delta 1.
Okay.
But when you compute, like there is this piece here is actually way larger than the diagonal piece.
I'm sorry, but that's from a computation, or is that something?
There is actually a systematic reason why. I mean, there is an extra expansion parameter that controls this.
So you're saying you can prove it?
I can prove. We have shown like that there's an extra expansion parameter that goes through this. That's not just delta 1. The whole point is that there is something analog to the logs here in this case that's not just delta 1. So there is something else here. And this something else is actually larger in this case. So in the
Can you give just a physical explanation?
Yeah.
I don't need a calculation, but just why?
Yeah.
Why should that be more relevant?
okay.
Especially because you have counter terms and all these things that are hidden. I mean, how do
No,
you
but
know?
okay. But the message is this. Now I'm going to explain why this
Okay.
why this off-diagonal piece is the most relevant one. But just to explain now what we can gain from this. So this means that if we use these ansatz that we have here, plug back these ansatz in a tree-level computation, if this guy is large, as we have shown, this absorbs the main part of the loops. And you don't have to go to cumbersome loop computations. You can just use this piece here, this ansatz, and this is the most relevant piece, way larger than this piece. Okay? So you can check definitely. You can. So this is something we checked with simulations. So the plot I showed yesterday is something that we checked with simulations. I showed the RG, and it exactly matches what we expect. And this is something we checked. Like the line that you saw is the RG prediction, and the points I was showing yesterday are simulations that we have run.
Yeah, but there
So
were
we-
extra parameters, right? So you checked by introducing extra parameters, right?
We
That's what you
checked
talked
it-
about yesterday.
Well, we introduced like the bias parameters, yeah. But
So
this
if you
is-
add more parameters, maybe you can adjust things so that it works.
no. I mean, simulations,
Okay.
it's exactly the same in theory and data. I mean, both have the same number of parameters. Okay, so you ask me, what's the reason for this? What's the physics behind this, right? So I'm going to explain you the reason why, what's underlying this, why the two loop is actually, what I call intrinsic two loop is larger than the one loop. Is smaller than the one loop square. Let me raise this part here. Okay, so in the next 10 minutes, I'm going to explain exactly the physical intuition why this region here is larger than this region here. So when we compute the solution of the bias as a function of lambda, we find that this is equal to a tree-level computation, B star, minus sigma square as one loop bias at a fixed initial condition. So star means initial conditions, okay? Plus, so there's a minus here, so there's a plus here, so you have a sigma to the fourth as one loop squared. And you have something here, which I call I, And you have something which is a sigma to the fourth, also sigma to the fourth contribution of lambda as 2 loop, I 2 loop. So those are just numbers. Those are just numbers, like order 1 numbers. So we want to compare how this 1 loop square piece compares to this 2 loop piece, right? So this is the tree level part. So this is the, so I mean, this is there are indexes here.
Sorry?
So this is a generic bias BA, and I'm summing over matrices here. So this is
okay.
A, B, B. I'm just omitting those because otherwise it's, okay. So it's a tree level, like there's a tree level piece, there's a 1 loop piece. So this is the 1 loop square. And this is the 2 loop piece, okay? Then consider for now we are in a universe that scales like that P linear, that's like the power spectrum of linear fluctuations, is proportional to K to some index N. I'm just assuming a cosmology that scales like that I know the scaling, the perfect scaling of this cosmology. When I check this I2 loop over 1 loop square, so the question is this guy large compared to this or not? So this is what controls basically the 1 loop, and this is what controls the 2 loop piece. Okay, so the question is how large is this guy compared to this? So when you plot I2 loop over I 1 loop squared, you find something like this. So this is, okay, so this asymptotes to, let me, it's an asymptote. This asymptotes to 2 over 15, so smaller than 1. And this is N, the cosmology I have, the cosmology index that I have here. And this line here, asymptotes here, N equals -3. And the reason for this is because the amplitude of the fluctuation, so it means, okay, first, it means that for different cosmology indexes, like for different powers of cosmology, basically this guy is always smaller than 1. And it's not just smaller than 1, but it asymptotes to, okay, either here something smaller than 1, or here something that goes to 0. And the reason for this is because when you compute those 1, 2 loop over 1, 1 loop square, it's actually proportional to something. So this guy, I2 loop over I1 loop square is proportional to its powers of N plus 3. Sorry. So 1 loop square, sorry. You can show this. So it means that there is some extra expansion parameter here, which is 1 over N plus 3. So this guy goes as 1. So this piece that goes as 1 loop square goes as this, while this piece here goes as 1, sorry, N plus 3. So there is a scaling with the cosmology index that you have. So this scaling with the index is what suppresses the 2 loop contribution. So what we have shown is that not only like delta 1 is an important expansion parameter, but the cosmology index that you have, like the powers in terms of the cosmology, like N, which is how the cosmology fluctuations evolve as a function of scale, plays an important role here as well. So it's not an expansion just in delta 1. There's an extra expansion in the parameter, like in the scaling index of the cosmology that you have.
It's not necessarily just a power law, right? In principle, there could be log, N plus log of K corrections or something, right?
So in this case, we find that it scales as this. For a scaling index, this is exact. We find that this is a perfect scaling we find.
I'm just saying, why assume just K to the N? It could be K to the N plus
Oh yeah,
log
perfect,
K.
perfect. So this is a power law universe, right?
Yeah.
But we don't live in a power law universe. So the next question is, for lambda CDM, that's our universe, how does it look like? So we did it as well. So for a lambda CDM universe, so the power spectrum is quite non-smooth for lambda CDM, right? So in reality, when you check the power spectrum as a function of k, it goes as something like this. You have the BAO WIGO, it's something like it has features, it has whatever.
Oh, I see. So this is actually even the power spectrum now, not.
So this is
not
the power
the-
spectrum now.
I see.
So for lambda CDM, it's more complicated, right? So what we did is to take the lambda CDM spectrum. Okay, now I'm confused with my things here. But we took a lambda CDM spectrum and we checked, okay, for the lambda CDM case, you can approximate the tail here as something that goes as k to the minus 3 log of k star for some fixed k star here, okay? So this is the lambda CDM spectrum in the UV piece here, okay? And we checked that for lambda CDM, okay, so this is for a scaling universe. But for lambda CDM, when you compute I 2 loop over I 1 loop squared, you find something like 48 over 125, 1 over log of lambda over k star. So for lambda CDM, we use this ansatz, which approximates the tail of the power spectrum. It doesn't absorb completely the features, but in the tail of the spectrum, it's again exact result. It's an exact result that goes as lambda over k star. K star being just an anchor scale that we have here.
It's dimensions.
K has dimensions here. It's an anchor scale that you use, but this anchor scale,
No, what I mean is log 1 over k star is what?
lambda,
lambda.
There's lambda, sorry. Lambda. So what I mean is, also for lambda CDM, there is some indication that the two-loop result, the intrinsic two-loop result, so pieces of the two-loop diagrams, like the diagonal piece, is actually small compared to the off-diagonal piece. Indicating that, again, there is an extra expansion parameter that's not just powers of delta 1. Like the usual case that you have. Right. So this is something that came out in this recent paper that we had in July. And now the plan is to apply that to data and see whether we can actually gain more information by doing this or not. Cool. I think this is what I had to say. The message is you can either go through these cumbersome loop calculations, and this is something I showed yesterday, that by going through 2 loops, you actually can gain some information. Or you can use the RG to gain ansatz like about the regions of these 2 loops. And there is an indication that the main region, like for the higher loop pieces, is actually the off-diagonal piece, which is already fixed by the lower loop calculations at some power that you can gain. Yeah, that's all.
I asked proof, and I guess you're giving me arguments, but do you have a proof that it's, I didn't understand. You're comparing with simulations, that's your main argument, or?
No, for a power law universe, this is exact.
No, power law, I agree, but then you're introducing a new, okay. Anyways, you haven't explained why these things have that dependence, but I can believe that there's some reason, but it's not for any universe, it's just for our universe that it's supposed to be true, or?
So this depends on how so in this case, the propagator of the theory is the linear power spectrum.
No, so I understand you might be able to prove it in this case with the power law.
Yeah.
That I can accept. Or with that, I can accept. But are you saying it's true for any dependence?
No, definitely not. So,
Okay, so your proof depends somehow on this power law?
so definitely. So in the case, whether the RG gives you information or not depends on the structure of the propagator of the theory.
Okay.
In the case of quantum field theory, it's just 1 over k squared or whatever you have.
Okay.
Here, the propagator is the linear power spectrum. So it definitely depends on the shape of the spectrum you have. So what I'm showing you here is that if n is too large,
Yeah,
actually, there's no parametrically small parameter you have.
I understand. And probably 3 loop, it's the same thing. It's I3 loop over I1 loop cubed or things like that.
So at 3 loop, you would have another direction here. I don't know. What's the letter we use as?
You don't have to draw. You just, I
So the question
assume
is-
that there's some similar equation you can write for I3 loop over I1 loops cubed.
Yeah, so the question is, you have to compute it and show that the 3 loop piece, the diagonal piece of the 3 loop.
So you don't have to compute. I thought this was just an argument based on the power law. There's no computation.
No,
to
but
do.
then now you need some hierarchically telling you that the 3 loop over the 1 loop cubic is small as well. And this,
Sorry, that's an equation, right? That's not a computation. That's an equation. That's an exact equation.
this is an exact equation.
So it came from a computation?
Yeah,
I see. But the computation is not very simple?
this is really simple, but the 3 loop piece, you have
It's
to
not this simple.
compute a triple hard limit. We didn't compute a triple hard limit.
Okay.
We did compute a double hard limit. So the 2 loop piece is given by the double hard limit. This is given by the single hard square.
But the computation is just that thing you're calling number, right?
Yeah, this is a number.
Yeah, so the number, of course, you have to compute.
Yeah, the
This
number.
dependence on n, I assume, is something very straightforward.
Yeah, that might be true actually.
Okay. No? I don't know, it's so simple for the 2 loop. I would have thought that it's just some counting argument. No?
Actually, yeah, maybe.
Okay, maybe my intuition is wrong. Any other questions?
So on a very general ground, so when you resound the logs, aren't you worried about subleading logs that should appear in the next order?
So they're definitely a next to leading log. I mean, the analog of the next to leading log.
Yeah.
But this, since we did the 2 loop RG, and I provided solution of the 2 loop RG, the next to leading logs are absorbed by the 2 loop RG, right? And this is what we already provide. We checked that they're small compared to the next to the leading logs, but in principle, we already have an equation for the next to leading log that you can use. So.
Other questions? Okay, so let's thank you.